at what height would I have to release the car over here in order for the car to successfully make it through the loop? I'm looking for the minimum height. Now, if you paid attention yesterday and you watched the video, you have an idea of what I'm asking. So I'm going to pause here. There's definitely a clear method for you guys to actually get your answer. So although you guys left and brought back a variety of them, there is a method. You could follow along with that method. We understand that we're going to have to bring 3 pieces of information together in order to solve for this problem. And what I'm seeing in your answer here belies a certain amount of understanding, but I can see where there's some mistakes here. Before we actually jump into this, please understand that this is not what you're going to have to do on the exam. Remember, we know the exam is not going to be incredibly heavily mathematics. There might be some theoretical stuff, sure, but they're definitely going to ask us questions that are going to tax us in a different way than this. Meaning, we have to understand this thoroughly, because the question they're going to ask is something more akin to, you go into your garage and pull out the equipment to make one of these, and then when you make it, you find that it doesn't meet your expectations. So then they're going to have some follow-up questions about what could be at play here. That's why understanding how it's supposed to work theoretically is only half the problem. The other half of the problem is understanding why it doesn't work this way in real life, and what kind of experiment you could do, or what kind of experimental apparatus you could use to be able to determine what's happening. So let's look for our expectation. Let's first do the theoretical case, the one that is straightforward, obvious, and has a procedure you could memorize in order to learn. So we're going to start with net force equals ma. That's the right place to start for this problem, because we know that this problem is about circular motion. I have a clear circle here. And if I remember correctly, we know that we have 2 forces acting in the same direction towards the center of the loop, and that, of course, is going to be related to my centripetal acceleration. So from here on out, I could look at the limits of the problem, but this limit is going to produce for me the limiting velocity the car has to have, what minimum speed the car would have to make it through the loop, and that minimum speed would occur when the normal force disappears. So that gives me mg equals mv squared over r. Now, if you paid attention yesterday, you realized that part of yesterday was about looking at ways in which we can speed up our time. And this is one of those ways. I'm not going to plug in numbers and get v. I know many of you probably did. I'm just not going to do that quite yet. What I am going to do instead is recognize that at this location, the car has both gravitational and kinetic energy. And wherever it started from rest, and I am suggesting it started someplace where it has all gravitational potential energy as well. How are we doing so far? No worries? All right, well, I'm going to suggest that we look at the fact that mgh minimum has to equal 1/2 mv squared plus mg times 2r. Let that soak in for a minute. Just making sure that it's soaking in for all of you. Is it? All right. Well, look, don't look at the numbers yet. If I look here, this velocity is how fast the car has to be traveling to successfully make it through the loop. That velocity and this velocity are the same velocity. So, instead of finding v, I'm going to just take a look at this and realize I could write this as mv squared equals mgr. Do you see what I've done? I just multiplied both sides by r. Now, it's a 1/2 mv squared here, so I could make this a 1/2. And now I could throw that over there and get mgh minimum equals 1/2 mgr plus 2 mgr. I know I got some confused faces there. Not too many confused faces, but a few. I'm just demonstrating a different way to do this. But this is going to also produce something I really, really need for you to look at. First, mg goes away on all of those. And I just get that h minimum is 2.5 times r. Of course, there's a lot to take in here, but it also tells me that I've done it for every single roller coaster there is. Right? Every roller coaster should obey this. Not just the toy one that I had set up on my table with a 20 centimeter high hoop. It's for every roller coaster that exists. Your lift hill needs to be 2.5 times your radius, as long as the radius is on the ground. Now, there's pluses and minuses to this, but first, that tells me that everybody in the chat window all of a sudden knows who's right and who's wrong. Because the radius was 10 centimeters, so this is 25 centimeters. But there's more than just that. Although, yeah, we've solved this for every single problem, every single hoop problem. All I've got to do to screw with that is not have the hoop start on the ground. Or something else similar to that. But what I really want to impart to you, the takeaway from this discussion is the exam writers know that this 2.5 times the radius thing exists. They know it. And they know that there's tons of people who could just memorize that. James, you have your hand up. Yep. No, you can do it that way. It's not a big deal. What I want to impart to you guys is that they're not going to ask this question on the test because they know it's a memorizable fact. But if you actually watch the video, you know that when I released the car at 2.5 times the radius, it didn't make the loop. In fact, I had to get above 30 centimeters for it to make the loop. If you watch the video, you know that that's true. The question comes down to why. Why do I have to start the car higher than theoretically necessary? And if you're thinking that you're going to get off by saying, well, friction or air resistance, you do understand that that's not how it goes in those tests, right? That you have to be able to explain how air resistance, how friction might affect your answer. But the bigger difference too is, and this is how real roller coasters work. Real roller coasters don't obey this principle at all. They don't even come close. And it has nothing to do with friction or air resistance. If you watch real roller coasters, and the Scorpion is the perfect example of this, because it's a perfect 360 loop started on the ground with a standard lift hill. And the standard lift hill is not 2.5 times the radius. It's lower than necessary, not higher, which should make you wonder how that's even possible. Because as I started out my discussion, there's real physics, and then there's what we tend to throw in front of you as pretend physics, and you've seen a lot of pretend physics. So how do we bring these things together? How do I get you to think apart from the example every time? Real roller coasters aren't a single car. They are a train of cars. Right? What's the potential energy of this system? Do I base it on where the lowest part of the car is? The center of mass of the system? The highest part of the car? You might jump to the idea that I'd base it on the center of the cars. Unfortunately, it doesn't really work, because when the center of the cars was at the top, half of the cars were beneath on either side. In fact, think of it this way. When the train makes it to the top of the loop, what's considered the train making it to the top of the loop? When the center of mass is at the top of the loop? Or when the first car is at the top of the loop? What's the top of the loop now? Real roller coasters, because they are trains and not just a single car, have to have different rules. Rules that deal with the fact that perhaps the center of mass of the system and the extension of the system also play a role in determining how you would design your roller coaster. So SheiKra operates much different than Kumba. And it has to do with the fact that SheiKra has only 3 rows. It's super wide, but it's only 3 rows. But Kumba and Montu, they each have 10 or 11 rows, which makes them much longer cars, which changes the entire dynamic of the system. Now, I'm not saying this is on the exam either. What I'm saying is you can memorize the box sliding down the ramp and going through the loop, and they know that. What they want from you is your ability to deal with a problem that is different than what you're given. I need you to be able to think outside the box about these and answer the questions in such a way that you understand what the model looks like and how the model is different. Look, I need you to nail the 25 centimeters on a problem like this every time. Not because the number is important, but because they're going to start there and going to change it in a way that's unusual. Now, I want you to be prepared for that. So that's all for today.